Hi, I'm Kaina, and my project has been on electron capture and ionisation in carbon 6+ collisions with helium. In atomic collision systems, there's a number of different things it can do. Electron capture is when the projectile, carbon 6+, comes and steals the electron of helium. We end with carbon 5+ and positive helium. Ionisation is when that electron isn't captured, so we end with carbon 6+, positive helium, and a free electron. One of the ways we can measure the probability of these different outcomes is with something called a cross-section. Atom-ion collisions have a number of different applications, particularly in astrophysics, looking at particle interactions in planetary atmospheres, plasma physics with modelling and diagnosing plasmas in reactors such as ITER, which is being built, as well as this, hadron therapy is an emerging form of cancer treatment which uses carbon 6+ ions rather than the traditional photons, because the heavy ions limit damage to healthy tissue. The wave packet convergent close coupling method is a way of analysing these systems. We apply the semi-classical approximation, which means that the heavy particles are treated classically and the electrons fully quantum mechanically. We also apply the frozen core approximation, which assumes that one of helium's 2 electrons is stuck in the ground 1s state throughout the interaction. This allows us to reduce the 4-body problem to 3-body by grouping that frozen electron with the nucleus to create a model potential that acts on the rest of the system. This is called the effective one-electron approximation. The scattering wave function is expanded for a number of target and projectile-centered pseudostates, which is then put into the time-independent Schrödinger equation and solved to produce a set of first-order differential equations, which are solved for expansion coefficients. Our results for electron capture and ionisation are shown in the red, compared to a number of other theory and experiments. Although the shape is generally correct for both, we do tend to overestimate at low energies. This is suspected to be because of the effective one-electron approximation, and to further investigate this, we will be extending it to the 4-body method, which considers both of helium's electrons independently to the nucleus, although it is much more computationally intensive. Further work will also be done to calculate the differential cross-sections, because currently no theory can explain the kinematically complete experiments that have been done. Through this project, I have learned a lot about the wave packet convergent close coupling method and how to apply it, as well as the derivations for a lot of the math behind the code. Finally, I'd like to thank my supervisors, Cade and Alicia, as well as the Pawsey Supercomputing Centre for their support. Thank you.